PreAP, PreCalculus. We're in notes 4.3. This is the second part of these notes. In the first part, we learned how to use the rational root theorem. Pardon me. We learned how to use the rational root theorem. We used how to use the rational root theorem to find roots that maybe weren't rational. We found some imaginary roots and we found some irrational roots. In each of those cases, once we found the quadratic that was left, it was really easy to solve that quadratic. All right, so we got a couple more examples to do. Consider the function f of x. What conclusions can you make about the four roots of the function? Explain your reasoning. Well, we can clearly see this is a fourth degree polynomial. So the fundamental theorem of algebra guarantees there are four roots because this is a fourth degree. F of x has two real roots, one positive, one negative. The graph clearly shows that. Each one of those has a multiplicity of 1 because the graph crosses the x-axis and does not change concavity. That means the other two roots, the ones that we don't have to be imaginary. Make a list of the rational roots. Make a list of the rational roots that the rational root theorem guarantees are possible. Once again, here's our function. We take the coefficients of 10, put them on top of negative 10, coefficients of 12 and put them on the bottom. So every combination of top and bottom numbers together would be the possible rational roots. From that list, we're supposed to make, let's read it. Which roots appear to be the roots from the graph? So here is one between 0 and negative 1. It looks closer to 0 than negative 1. So that could be maybe a negative third, maybe a negative fourth, maybe negative 1/6. I'm going to say it's negative 1/4 based upon how this graph looks. So a highly possible rational root, I'm going to say it's negative 1/4. Let's say I end up being wrong. Well, then I could check negative 1/3 or negative 1/6. And if none of those work, then this is actually an irrational root, which is possible. This one here looks like it's bigger than a half. So if it's bigger than a half, maybe like a 2/3 seems like a reasonable thing. If I broke this into 3 equal parts, 1, 2 of the 3 parts, if I'm wrong, it's no big deal. We can fix it. So I'm going to take my polynomial, as the directions say, perform synthetic division to verify that they are in fact roots. So I take my my coefficients, 12, 19, 48, negative 29, negative 10. I'll divide it by negative 1/4 first. If it works. If it doesn't work, I gotta try something different. So I add negative 1/4 of 12 is negative 3. If I add those, I get 16. Negative 1/4 of 16 is negative 4. If I add those, I get 44. Negative 1/4 of 44 is negative 11. Add those, we get negative 40. Negative 1/4 of negative 40 is 10. The remainder is 0. I am comforted knowing that I am on a hot streak of predicting what these highly possible rational roots are. And then divide that by 2/3 synthetically. Hopefully this works. So 12 and 0 is 12. 2/3 of 12. You can do this in a couple different ways. You can say 2 times 12 and then divide by 3. Or you can take 12 divided by 3 and then multiply by the 2. I'm going to do 12 divided by 3 is 4, times 2 is 8. Add those, I get 24. 24 divided by 3 is 8, times 2 is 16. If I add these, I get 60. My numbers are getting huge. 60 divided by 3 is 20. 20 times 2 is 40. And that, once again, is comforting because the remainder is 0. Over here, I'd written remainder 0. Or you can just write 0. So here's what we know. This function's name was f of x. Since negative 1/4 is a 0, x plus 1/4 is a root. This is the factor theorem. Since 2/3 is a 0, x minus 2/3 is a root. And now we're left with this quadratic, which is 12x squared plus 24x plus 60. Now to make this simpler, I'm going to factor a 12 out of this because that's a GCF. I'm going to put that 12 all the way in the front. So f of x is equal to 12 at the sum of x and 1/4, the difference of x and 2/3, and then I'm going to have x squared plus 2x plus 5. We just divided a degree 4 function twice, so the resulting polynomial is quadratic. The remaining roots solving that quadratic are going to be imaginary, and let's see how this works out. So I got x squared plus 2x plus 5. Now I didn't know these were going to be imaginary. Actually, I did know that. Because if you look at the original picture, we said at the beginning, hey, we got 2 real ones, that leaves 2 imaginary ones. We would like to factor this, but I can't think of 2 integers that multiply to get 5 and add to get 2. So we're going to use the quadratic formula. And when I use the quadratic formula, I always find the discriminant first. Discriminant's b squared minus 4ac. B is 2. A is the lead coefficient, and C is the constant. So that's 4 minus 20, that's negative 16. This confirms what we suspected, which was we're going to get 2 imaginary roots for this because the discriminant's negative. That means we're going to get imaginary answers. So to find those answers, we use the quadratic formula. X equals negative b plus or minus the square root of the discriminant over 2a. b is 2, so we have a negative 2 plus or minus the square root of the discriminant, that's a negative 16, over 2 times a is 1. The square root of negative 16 is 4i. 2 times 1 is 2. We can divide both the terms in the top by 2, and we're going to get that x is negative 1 plus or minus 2i. So to write down all the roots of this fella, we got negative 1/4, 2/3, negative 1 minus 2i, and negative 1 plus 2i. So this is the first example that we've done in this chapter where we had to use the quadratic formula to solve the quadratic. All right, on the flip side, based on your results from the previous pages, provide a plan on how you would find all the roots of the polynomial function. Let's see if I can cheat a little bit here. And cheat I will. So let's walk through this. We start with a polynomial, and our first choice is we'd like to factor this. If we can factor it all the way, and then we set each factor equals 0 and solve it, we're finished. If we can't do that, then perhaps we should use the rational root theorem. Find the possible rational roots. If you're given a graph, look at it, find the highly possible rational roots. Use synthetic division to divide down to a quadratic. Once you have a quadratic, you take the quadratic, and if you can, if it's in this form, get x by itself by subtracting b, dividing by a, and then square rooting it. If that doesn't work, in other words, if it's not in this form, factor it. If you can't factor it, complete the square. If completing the square seems like it's difficult because lead coefficient isn't 1, then you can use the quadratic formula. So essentially it's factor it and then solve, use the rational root theorem, divide synthetically to get down to a quadratic, and all this is saying solve the quadratic. There are 4 different ways that we could solve it. All right, we got 2 more examples to do, and we've taken the gloves off, and it just says find the roots, real or imaginary. So let's see if we can do this. Now it looks like at first glance, maybe concavity changes. I'm saying maybe because I'm not 100% certain. It looks like it might there, but maybe it does not. Let's find the possible rational roots. Take the coefficients, take the factors of 6, put them in the top of the fraction. Take the coefficients of 3 and put them in the bottom. The only real root that this has is negative, and it looks like maybe it's negative 2/3. So we have an option. We do have an option for that. So I'm going to say that our highly possible rational root is negative 2/3. Now, if that's the case, either this is a rational root 3 times, or it's a rational root 1 time, and the other 2 are imaginary. Let's see. So I'm going to take coefficients 3, 8, 13, and 6, and divide it by negative 2/3 and see if it goes. If it goes once, maybe I'll try it a second time, see if it goes again. Add, when I multiply negative 2/3 times 3, the 3's cancel, I get negative 2. I add, 6 divided by 3 is 2. 2 times negative 2 is negative 4. If I add these little fellows, I get 9er. 9 divided by 3 is 3. 3 times negative 2 is negative 6. So that worked. Maybe this would work again. I'm just going to try it. Whoops. It's negative 2, 4. Oh, now I'm in trouble. It's going to give me negative 8/3. So it did not work the second time. So here's what we know. We know that g of x factors into an x plus 2/3 and 3x squared plus 6x plus 9. To make my life easier, I'm going to factor a 3 out of these terms. Put it all the way to the front, because that's usually how we write coefficients. This looks like it could factor, but it doesn't. Two real numbers that multiply to get 3 and add to get 2? I don't think so. So we are going to have to see if we can find these roots using the quadratic formula, since it doesn't factor. We could complete the square. Should I remind you how to complete the square? Might as well. Let's do that. I've showed you the quadratic formula. Let's complete the square. Why might you complete the square? The lead coefficient is not, or the lead coefficient is 1. To complete the square, we want this to be a perfect square trinomial. To get that to be a perfect square trinomial, we're going to take half of 2, which is 1, and then square it. That assures us that this right here is a perfect square trinomial. You can't just add 1 to an equation. You have to also subtract it from the equation to balance it out. So now we've added a +1 to this and a -1 to this. We haven't changed the value. We just changed the way this looks because that's 0. This is a perfect square trinomial, which factors into an x plus 1 quantity squared. If I add these two together, I'm going to get 2. If I subtract 2 from both sides, I get the sum of x and 1 squared equals -2. If I then square root both sides, I get x plus 1 equals plus or minus I square roots of 2, because the square root of -2 doesn't go evenly, but you can take the -1 out and make that I. And then this is x equals -1 plus or minus I square roots of 2. That's completing the square. Had you used the quadratic formula, you would have got the same thing. All right. So what are the roots? We had -2/3. We have -1 minus I square roots of 2, and we have -1 plus I square roots of 2. Last problem. Directions, find the roots. So let's list the possible rational roots. Take the factors of 3, which are 1 and 3, and the factors of -6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Let's see, this looks like this one right here might be 1/2. Is that an option? It is. So my highly possible rational roots. Well, on the right looks like it's probably 1/2. This one here might be -1/3. Is that a choice? It is. I don't think we're changing concavity anyplace. So I'm guessing that each of those have a multiplicity of 1. If that's true, and then I just realized I said 1/2 over here. This is 1/2, which would be 3/2. That is also an option. So let me change this to 3/2. So -1/3 and 3/2 or 1/2. I think those are likely. So let's take and let's divide. Our coefficients are -6, 1, 4, 10, and 3. I'll divide by 3/2 first. -6 divided by 2 is -3. -3 times 3 is 9. Add. 10 divided by 2 is 5. 5 times 3 is 15. Add. Did I mess something up? I did. Picklesworth. -6 divided by 2 is -3. -3 times 3 is -9. I need to backtrack. I made a mistake. 1 plus -9 is -8. -8 divided by 2 is -4. -4 times 3 is -12. And then I add. Hey, same answer I just got. So I must get the same answer here. Add, I get -2. -2 divided by 2 is -1. -1 times 3 is -3. So that works. Let's try -1/3. -1/3 of 6 is -2. -8. Sorry, I made another mistake. This should say -6. -1/3 times -6 is +2. -8 plus 2 is -6. -1/3 of -6 is 2. -8 minus 2 is -6. -1/3 times -6 is 2. So that worked as well. So this h of x factors into an x minus 3/2, x minus 1/3, and a negative 6x squared minus 6x minus 6. Let's factor a 6 out of this. In fact, let's factor a negative 6 out of this. We get negative 6 times the difference of x and 3/2 times the difference of x and 1/3 times the sum of x squared and x and 6. That's not true. X squared plus x plus 1, I divided each of those by negative 6. I could complete the square here once again. I'll use the quadratic formula again because you're more likely to be using that. Most people hate completing the square. So let's find the discriminant. It's b squared minus 4ac. You need to write that down every time you use it. b is 1, a is 1, c is 1. So that's 1 minus 4, that's negative 3. Well, guess what? We're going to have imaginary roots. We suspected that. Take the quadratic formula, which is x equals negative b plus or minus the square root of the discriminant over 2a. Write down that every time you use it. Our b is 1. Discriminant's negative 3. And our a is negative, not negative, positive 1. That's going to give us negative 1 plus or minus I square roots of 3 over 2. So our roots, we got from the rational root theorem roots of 3/2, negative 1/3. I prefer to write those in ascending order. I didn't do that just now. Negative 1 minus I square roots of 3 over 2, and negative 1 plus I square roots of 3 over 2. This concludes this section. Please do the homework that goes with this in section 4.3. Thank you very much.